All right, so Foundations of Math 20, 6.3, this is going to be part 2, creating and solving systems of linear inequalities. So in the first part of 6.3, we talked about systems, what systems were, basically two or more inequalities that you graph on a plane or that you deal with anyways, all at the same time. And the regions of the inequalities, the regions that overlap, are the solutions to the system. And of course, there's going to be multiple solutions because as we took a look at earlier, all of the solutions in this area would be solutions to this system of inequalities. So this is the lesson that we did from first part of 6.3. So today what we're going to do is we're going to take a look at how to create this system. So now we need to kind of back up a step, take a look at a word problem, and how to generate the proper inequalities, then graph them and solve them. So that's what this example is going to be. It's going to be part 2. So I asked you to copy this down. You should have this in your notes. It says a car company can make up to 16 cars a day in their factory. They have to make at least twice as many 4-door cars as 2-door cars to meet the demand. Okay? So I guess the rest of this question would be, this is the situation. So a question that we might be able to answer to this are, and we'll just add this, what combinations of 2 and 4-door cars can be made at the factory? All right, so that's the kind of question that we might be able to answer. How many of each? Now, you could trial and error, sort of just pick a combination. Let's say, how about 10 of one and 8 of the other? And, does that fit the question? Well, you wouldn't get very far, and you could say, well, 10 and 8 is 18, so that can't be a combination. That can't be a possible answer because I can only make 16, or they can only make 16 a day, right? So obviously we could do trial and error, and we could come up with some different options. But this is a simple example. I realize that. So we probably could come up with a lot of different options right away. But let's work through the process of generating these inequalities, graphing them, and then you'll be able to see visually sort of where those combinations of these two types of cars that could be made at this factory will be. So the first thing we need to do is we need to generate the inequalities. Okay? So a car company can make up to 16 cars a day. Okay? So up to 16 cars a day in the factory. They have two kinds of cars, 4-door cars and 2-door cars. And there's some information about that as well. So 16 cars, two types of cars. What we want to do is we want to make an inequality and with variables. It would be a good idea to formally or informally set your variables. So let's say we did F as 4-door cars. Okay. So you want to set your variables in this inequality, either, like I say, on the side formally or informally. If you use just X and Y, that's okay, but you might get confused as you do the question, and especially at the end, you don't want to get confused as to which one is which, right? So it makes sense to choose a variable that fits the questions. So why don't we do T then as 2-door, right? 2-door cars. Okay. Now we can make up to, or I say we, but the company can make up to 16 cars a day. So that is equaling 16 as a max, or anything less than 16, right? So they can make less or equal to 16. So any ideas on what kind of inequality, because it's going to be our first one, kind of summarizing that information? Any ideas? Want to shout it out? Two types of cars, F and T, and the company can make up to 16 cars a day. So what's the rest of this? 4-door cars plus 2-door cars, what? Less than or equal to 16. Yes. Everybody see that? Okay. So usually with these questions, the first sentence has one of the simple equations or inequalities in this case. Okay. The next sentence, oftentimes, is the very next sentence, gives you some more information to add on here. So if we just have F plus T is less than or equal to 16, well, I mean, if that's it, then we have a lot of different combinations that could be made, right? So what's the other information here? So they have to make at least twice as many four-door cars as two-door cars. So you have to be real careful with this one. I'll just give you a hint. At least twice as many four-door cars as two. You have to be real careful because you might say, oh, twice as many four-door cars. That's 2F, and 1T, and they have to be it's less than or equal to, or whatever, or greater than or equal to, and just throw it out there. You have to be careful that the inequality makes sense. Okay, so let's just say that twice as many four-door cars. So let's just go 2F. Has to be, let's say, greater than or equal to T. Now, does this fit that information? So you have to be very careful. So this side is greater, right? So I need 2 times as many, 2 times the number of four-door cars is greater than the number of two-door cars. Does that make sense with the question? Which one, if this was an equation, okay, if this was an equation, which variable would be the larger one? Come on there, pen. If these were equal, which one has the greater number here? T or F? T has the greater number because in order for them to be equal, you have to double F. So we need more four-door cars. So this, right away, you can say, no, that's not going to work because F has to be the larger one. Okay? So in order for these to be equal, so that's at least as equal, then we need to have 2T. Okay? Because the two-door ones are not as plentiful. Okay, is this making sense so far? You want to start to build this? So how do these compare? I need at least twice as many four-door cars. So which one here is bigger? Which one in our inequality should be bigger? Is this a greater than or equal to, or is this a less than or equal to? The equal to says that the number of four-door cars is equal to double the two-door cars. So I need at least as many four-door cars. That means I can have more than double. Does that sound right? I can have more than double. So this is going to be greater than or equal to. Okay, do you agree with that? Does that look right? Do you have any questions about that? So the number of four-door cars is going to be equal to or greater than double the number of two-door cars. That's what this sentence says. At least twice as many four-door cars as two-door cars. Okay? So there's our two inequalities. We're going to set those up. We're going to graph those. And then we're going to see where our feasible region is. You remember I think we called that a feasible region last lesson, didn't we? Feasible region. That's the region which fits the entire question. Okay, so let's just take a moment to draw a coordinate plane, and let's start sketching these things here. Okay, so what's our domain? When we set up our coordinate plane, what's our domain? So what is it, like can we have negative numbers for any of these variables? No, we can't make a negative amount of cars, right? So we don't need negative x or negative y on this coordinate plane, or negative f or negative t. We don't need that. So right away, you can kind of start to simplify things by just saying, you know what, I'm just going to use the positive domain for each of these variables. Okay? Okay? Now, it would be a good idea to label our axes. Usually they're x and y, but we have f and t here. So why don't we go f up here and t down here. So this axis would be the number of two-door cars on the bottom here. So two-door cars, that's the number of them. And over here is number of four-door cars. Okay, is everybody with me so far? Okay. Now you can rearrange these equations, I guess, right? You can get them into y equals mx plus b, or in this case it would be f equals mt plus b. We could do that. You don't have to. You could just generate some numbers here. Like for example, if I had 0f or 0t, I would have 16f, right? So that's going to be a point. 0 and 16. The other one, of course, 16 0, right? So if this is 16, let's put 16 over here. So this is the point 0, 16, this is the point 16, 0, right? And obviously 8 and 8, so we do 8 and 8, you know, you put that up there too, and you know, 2 and 14, and so on. And so you can kind of see that we are getting a straight line here. Now, here's a question, okay? Is this line solid? Is this line solid or not? What's your thoughts on that? Do I make this a solid line or something different? Yes. Okay. Anybody agree with that? It's or equal to. I guess the only issue is, you know, are we okay with making a third of car, having that completed by the end of the day? You might argue, well, you could pick it up the next day, I guess. You could have 16 or 15.3 cars made, I don't know. So probably, in this question, probably we would want to consider this being like a dotted line. So it just, and I don't have all the lines here, but if you kind of did this, a dotted line to signify that, you know what, we're only interested in whole numbers of cars. So F is an element of whole numbers, and so is T, an element of whole numbers. Because we can't have 0, right? We could make 0 of something and 16 of the other. That's okay. Yeah, good?
Does the dotted line equal to and then like the dots in the shading?
Yes, the dotted line here means that the line itself is included, because we do have or equal to here, but we're not considering like a 0.77 of a car. So it's just the whole number values for those.
What would it be then if this wasn't?
Okay, if it's not included, you'd do a dashed line. So like a dotted line would be like on the, see, I don't have the cross, you know what I mean? But if you have a coordinate plane like this, it would be, the dots would be on the actual intersections of the lines there. And then the other one, technically, if you didn't want, it would be a dashed line, I guess. So dotted like this would mean whole numbers, and those are okay. Dashed means up to, but not including that line. Good question, though. And in the textbook, I think they use different colors and everything, too, which, forget that. All right. Okay, what about this one? F is greater than or equal to 2t. Okay, so remember we've got F is y, so this is kind of like y equals 2x. Right? That's the line we're looking for. So again, if we have 0, 0, is that going to be on the line? 0, 0? Does 0 equals 2 times 0? Yep. Okay, so if we have x of 2, right, then what is y? 4, right? If we have x of 4, y is going to be 8, and so on. Okay? So we basically have this line here with a slope of 2. What combination here is going to be on both lines? Is there a combination of cars that are going to be on both of these inequalities? And we haven't done the arrows yet, but I'll get to that in a second. Is there going to be a number that's on both lines here?
No.
Someone says no? Okay. Is there a number t and f that adds up to 16 that fits this? Okay, I'll give you a second to think about that. I want a yes or a no and a why. But let's go back to the inequalities. Okay, let's shade the regions. So this one is less than or equal to, for the first one, for the red one, it's less than or equal to. And so is 0, 0 in that region? 0 plus 0, is that less than 16? Yes. So we're looking for this way. Okay. And let's test, well, 0, 0 looks like it's on the line there. So let's test something else. Let's test 2 and 10, let's say. Right? 2 and 10 would be in this region somewhere. Or even 0 and 10. Let's do 0 and 10. Okay, at this point right here. So 0 and 10. Does this work? Is 10 greater than or equal to 0? Yes. Is everyone understanding what I'm doing with these test points? Yeah? Okay. So you see how we have this right here? So the shaded region, if I now get rid of these arrows here, the shaded region, oops, Didn't want to get rid of the axis there. So the shaded region is going to be in here. Now, again, these are going to be points, right? We don't want fractions of cars, so again, those are going to be points. But that's the region in here that overlaps. Okay? All right. Back to the question, is there a point that lies on both lines? Yes, no? Okay, let's do cars. What are the numbers of cars that add up to 16? Okay, 10 and 6. Okay, so 6 times 2 is 12, not 10. Okay. What about 5 and 11? No, that's not double. 7 and 9. Nope. Okay. So there's not one there. How do we know for sure? One of the ways you could do this is get on the graphing calculator. Okay? So you guys can use a graphing calculator for this, especially to find intersection points, because that's going to be important. So let me just show you how to do that again. Okay? So graphing calculator, you want to get to your y equals screen, and I'll maybe hand these out in a bit. But you want to put these equations in. Now the calculator, you have to get this into y equals mx plus b for the calculator. So this is going to be f equals negative t plus 16. That's going to be y equals negative x plus 16. So that's the one you're going to put into the calculator there. And this is going to be y equals to x. So you're going to put those ones into the calculator. Do that over here. Negative x plus 16 and 2x. So if we graph those, what do we see? Okay, so here we go. Got to change our window. Let's get some more y-axis in there. So the y max, let's up that to 25. I could decrease my y minimums as well, and my x minimum, I guess. I don't need the negative values so much. Okay, so there we go. It's coming. All right, so it looks like we've kind of drawn our lines fairly well. Let's see what this point is, and let's see if they're whole numbers. It doesn't look like it's going to be, right? Does anyone remember how to find intersection points between two lines with a graphing calculator? Calculate. Second function, calculate screen. You do number 5, intersect. It'll ask you for the first curve, say yes. Second curve, say yes. Do you want me to guess? Yes. Okay, so 5.33 and 10.66. So if we're only interested in whole numbers of cars, there isn't going to be an answer right there at that intersection, okay? Because they're decimals. But we can still answer our question, what combinations of cars can be made in the factory? So basically you're looking for any combinations that can be, that will be in this region. And what are a couple examples? So what are points in this region right here? 2 and what? What's a point that's in this region? 2 and what? 2 and 4? Okay. So 2 and 4 is going to be right on the line here. Yeah. Anything more than 4 as well, but that doesn't go over 14, I guess, right? So 2 and 10, 2 and 11, 2 and 5, right? Okay. So you could do 2. Come on. Whoa. 2 2-doors and 2 2-doors, and you could do, up to 14 4-doors, right? And so on. And you could list a whole bunch of different points that lie in this region. Back to the graphing calculator. I guess what you could do is you could kind of say, second function, calculate a value and find out what x to 5 is here. Okay, so 5 and 11 is on one of these lines. 5 and 10 is as well. Okay, so that's getting pretty close to this. So if you backed this off and said maybe 4, right? 4 is 12 here, and 4 is 8. So between 8 and 12, you could do 4 and 9, 4 and 10, 4 and 11, right? 4 and 12. So any of those work, and so on. I think you could just go ahead and move your cursor over here and find out what numbers are close to anything in here. So 2 and 8 work, right? and 2 and 12 work, and so on. So that's the way you can use the graphing calculator as well. Okay, any questions about that? About that example? All right, so just in summary real quick, what we want to do is we want to examine the question, make your inequalities, 2 or more that are given in the question. You want to graph them, shade the feasible region, determine for sure whether it's whole numbers or all real numbers or whatever that can be part of the solution, and then answer the question, whatever that might be. So that's what we did here in this question. That's something that you're going to have to do in this section. If you want the calculator to show you the feasible region, you can actually do that. This is how you do that. You go over to, not that one, but you go over to this right here. Okay? And I think you hit enter. Yeah. You hit enter until, you see this one right here, it's hard to see, but it's going to shade everything above that line. Okay? And so what we want to do, because we understand the problem, we want to shade everything below the line. Okay? And so if you graph that now, look what happens. So it kind of shades the region, so you can kind of see that a bit better. And then when we do the same thing to the second line, then you can see where the feasible region is. Is it over here, or over here? Okay. So keep hitting enter until you, whoops, too far now. Okay, so we graph that. There's the first one, inequality. It's everything less than. And then here's everything greater than. So the overlap, the hatched line there, that area, that's where you're looking for. Okay? And if you hit trace, you can kind of go through there and find points. Okay, questions?